Hello everyone! This is the first of a series of videos dedicated to solubility and complex ion equilibria. We're going to be looking at some definitions. We will study what's dissolution, what's solubility, what's precipitation. We will also be studying something called the solubility product constant, what it is, why we care about the solubility product constant, and we will also learn how to perform calculations using solubility product constants. And finally, we will look at the effect of changing pH or the presence of ions in solution and how those affect the solubility of a particular compound. As usual, this topic is separated in several videos to make it easier to follow. Let's start with some definitions. First of all, what is solubility? Well, we can define solubility as the greatest amount of a particular substance that will dissolve at equilibrium in a particular volume of solvent and at a particular temperature. And for example, I've got here the solubility of silver chloride in water at 25 degrees is this particular value. And you can give that in various units of concentration. I've got here grams per liter or molarity. So it depends, solubility depends on the substance you're looking at, what solvent you are using and what quantity of solvent you are using and the particular temperature that's happening. In general, solubility of compounds tend to increase with temperature because the process of dissolving a compound in a solvent is an endothermic reaction. So heat, increased temperature, favors the formation of the products, which is the dissolved substance. That is not always the case, and you have substances, for example, like sodium chloride, which solubility that's not really affected by temperatures. It's roughly constant at changing temperature. And other compounds, for example, cesium sulfate, in which solubility decreases when you increase the temperature. When studying the solubility of substances, we look at two processes which are complementary and opposite. You've got the process of dissolution, which is the process by which a particular substance will dissolve, and then the process of precipitation, which is the formation of the solid substance from a solution, so the reverse of dissolution. And precipitation is a very useful technique, and we use it a lot. It has many applications. It has life, there are many examples of precipitation in real life. Limescale that forms in your boiler or your kettle, kidney stones, the formation of stalactites and stalagmites. We also use it as an industrial process. So, for example, precipitation of compounds is a very important purification process, and we use it a lot, especially if the solid is formed as a crystalline solid. And the process of precipitation forms minerals, and dissolution, dissolves, remove them from solid form. Also related to solubility is the concept of saturation. We say a solution is saturated when you have a compound which is dissolved in a solvent, and the dissolution precipitation equilibrium, so there is an equilibrium between the substance in its solid form and its dissolved form. And as in many cases in chemistry, this is a dynamic equilibrium. And, the solid is dissolving and the dissolved solid is precipitating, but they do it at the same rate. So that's why you end up with an equilibrium. So the rate of dissolution is equal to the rate of precipitation. And we talk about unsaturated solutions, which is a solution of a particular substance that is not at that saturated point. The concentration of dissolved solid is not sufficient to cause precipitation. You are not near that equilibrium point. We can classify ionic materials by their solubility. So you have from very soluble ionic materials with a solubility of more than 10 grams per liter, insoluble ionic materials, which is the ones that have solubilities of less than 0.1 grams per liter, and then you have an intermediate category, which is the slightly soluble materials. A process of dissolution, precipitation, saturated solutions, non-saturated solutions, they're all around us. You have from the formation of limestone in limestone caves the formation of kidney stones, for example, which are due to the precipitation of calcium 2+ salts in our kidneys. And also, solubility issues play a huge role in the pharmaceutical industry, and they impact the viability of a particular compound to act as a pharmaceutical drug, and the delivery mode of that drug, how we give it to the patient. This is a really interesting paper from 2019 in which the author discusses what she calls the solubility conundrum. And the author talks about how when you are designing a particular pharmaceutical drug, you need to play with various issues. You need to make sure that your compound is selective and specific, but on the other hand, you need to make sure that your compound is soluble, is sufficiently soluble, so it can act as efficiently in the body. And also, related to the delivery mode, it also discusses how it's not only solubility that we care about, it's also permeability, especially when we are looking at compounds that are designed to be ingested orally, and how we need the compound, yes, to be soluble in order to be absorbed, but also be able to go through the intestinal wall. So intestinal permeability is another important factor that we need to consider for pharmaceutical drugs, in this case the ones that are designed to be delivered orally.